So what are these resolution strategies? We do the merge automatically for you the best we can. And of course, if there is a real conflict like changing the same data on the same entity, we have to find a rule, and the rule is the last one that talks win. You resolve the change on the server side on AWS Lambda in the cloud, and you resolve the change, the conflict on the client side inside your iOS application. That's basically the three options you have to resolve strategies. I'm going to talk about offline, which is a bit paradoxical if you think about cloud being offline for cloud. That's not the first thing you would think about having a cloud-based backend. And I will talk about data synchronization as well, because you're not staying offline all the time. At some point, you're going to be back online, or the user is going to be back online. So obviously, you need to reconcile whatever changed on the backend while your user was on the front end. And this is usually where you start to scratch your hair and you start to have white hairs like me as well. So detecting when the user is offline and reconciling the data. So first, when I mean offline, I don't mean to have the entire application working offline. Part of your application might work offline, and some feature might not function correctly when the user is offline. It's perfectly valid. So it's up to you and your product manager and the team to define what is the subset of functionalities you want to provide when your user is offline. It's perfectly fine to have some things that are not working. So we're talking about a subset of the application and not the entire application here. And if you want your user to continue to work with your application while the application is offline, it means that somehow you need to bring back part of the data set to the client device, so that there is like a cache or database on the client device. Yes, you agree with me? But if you do that, you create a partition in your data. Remember a partition? Remember, how many of you knows the CAP, C-A-P, CAP theorem here? Nobody? Okay, CAP stands for C, it's consistency. Think about the triangle. C is consistency, A is availability, and P is partitioning. Partitioning means that your data is split between multiple locations, like multiple databases. And if you have a cache or a local database on the device, it's a partition. You have a partition on your data. And what the CAP theorem says is that if you have a system that has to choose between consistency, availability, and partitioning, you can only choose two. So think about the triangle. You choose 2 points of the triangle, but you cannot have consistency and high availability and partitioning. So here we have P with partitioning, with a local copy of your data there. So what is the other one we are going to choose? Consistency or availability? We choose availability. I'm going to show you why and how you can compensate that to preserve the consistency as well, how you can recover for consistency in case there is some disruption between the data on the server and the data that you have in the cache locally. Okay? You guys still have everybody with me? Maybe I should add a slide with the CAP theorem and the triangle and something like that. But at the end, what you want is to provide a consistent end user experience. User is using your application at unexpected place. They go under a tunnel, in a train, in a plane, and they expect to have part of the application still working while they are in a plane mode, airplane mode, or while they are going under a tunnel, and then they can recover with the data a bit after. And part of that also involves real-time communication. In modern 21st century application, you expect your application to communicate real-time, see the change that other users are doing directly in your application. So let's be clear here, I'm not talking about nuclear power plant real-time or Airbus or Boeing real-time. I'm talking about real-time for business application here. So close to real time, a few milliseconds, maybe a few seconds latency is perfectly valid here. We are not controlling planes or flights as well. But we want our data to be synchronized across our device. How can you do that? How can you do that inside your web application, Android, iOS, and web application? So that's the subject of this talk, real-time, offline, data-first application. By the way, I'm Seb Stormacq. I'm working for AWS since roughly 10 years now at different roles. I was technical trainer, I was solution architect in the Alexa team when we launched Alexa in Europe. I'm now part of the developer relation team working exclusively on Apple technology, so iOS, Swift on the server side. I'm spending a lot of time trying to deploy Vapor application or Swift on AWS Lambda, which is quite fun as well. And there was another talk just before this one about Swift on the server side as well. You can find me on usual place, Twitter, as long as it still exists, GitHub, but of course Mastodon, LinkedIn, and all the others. I'm going to talk about 2 cloud technologies to implement this data first, offline, real-time synchronization for your data. I'm going to use AWS Amplify and AWS AppSync. So AWS Amplify, it's an open source library that you can include inside your application for Android, for Flutter, for iOS, obviously, for web. That makes it easy to access a cloud backend, an AWS cloud backend. Someone asked me yesterday on the booth over there saying, hey, I'm deploying on the IBM cloud. Can I use AWS Amplify? And not as of today. That won't be easy. So if you're using the AWS cloud, Amplify is probably the way you want to access your backend services from your application. It's free, it's open source, and AppSync, it's a managed service for GraphQL API. GraphQL is one way to make your API. I know there are others. You're probably familiar with REST, with gRPC. GraphQL has a couple of advantages over REST. The granularity of the data that you bring back on the client is one of them. The ability to query multiple data sources as well, it's another one. So these are the 2 technologies I'm going to use. But before talking about how it works, I would like to show you the result. So a very simple demo. I have a video fallback here just in case the demo is not working, but let's try to do the demo live as well. So I have a sample podcast application that shows a list of podcast episodes. Yeah, that's really, and for each episode, that will not be easy that way. For each episode, you have, for each podcast, you have a corresponding list of episodes. All of these data are coming from a GraphQL API on the backend, and all these applications are synchronized in real time. So if I add a podcast episode here, it should appear on the other application as well. If I add a podcast episode here on my mobile phone, which is connected to the same backend, yes, here I should select this podcast too. It should appear on the other one as well. So I have kind of real-time synchronization. Here you cannot see my screen, but it's the same app running on my device. If I delete the podcast, it's deleted from the other as well. And if I go offline here for a short period of time, let's go back here. If I can find the mouse, I turn off the Wi-Fi here. I turn off the Wi-Fi here. I continue to change things on my phone. You cannot see the screen, but trust me, I am adding new stuff there. The Mac is offline right now, so it does not receive the update. I enable Wi-Fi again, and in theory, after a few seconds, you can see the synchronization happening and the data being synchronized between the app. So all of that is super simple to do in terms of code, and I will show you a lot of code in this presentation, but it's just a few lines of code that allows to synchronize the data between the device like that. Really, literally 3 or 4 lines of code, nothing more than that. So we talk about the why, because you are developing modern application, your customer are using application from the top, biggest, largest company in the world, like TikTok, Instagram, and others. They are used to this type of behavior, and they expect the same from your application as well. But the reality is that networking is slow. Did you experience a network here today? Or sometimes non-existent. You might be in a plane, you might be in a tunnel, and there are tons of places on this planet when there is no network. But you want to provide a good user experience to your customer. So what are your challenges to provide offline access to your application and data synchronization inside your application? One of them is caching. What type of technology are you going to use to have a partition of your data, a subset of your data locally on the client device. If you think about caching, most of the time it's a key value store, like I write code to query my cache. If the data is not in the cache, then I query the database, then I need to push the data inside the cache. That's a lot of code that you have to maintain and to write to keep your cache consistent with the rest of the world. And a cache is not a database, so you cannot query your cache. You cannot make a select from where with a filter on your cache most of the time. It depends on the caching technology that you're using, and the cache is not real-time, and you also want real-time type of communication between your client application. How are you going to detect that there is a conflict? I'm coming back online, and someone changed an item on the server with his app, her app, while I was offline. I come back online. I also change the same data. How can I detect, just detect, I'm not even thinking about solving the conflict, but just detecting that there is a conflict. And if you detect that there is a conflict, how are you going to solve that conflict? Remember, you don't have consistency, so it's up to you somehow to solve the consistency paradigm and the resolution. And of course, your product manager is behind your back because it has to work across your web application, your Android application, your iOS application. Here I did the demo just with iOS, but I can do the same demo with a web application, an iOS application, and an Android application. And of course, you expect to have a lot of success with your application, so you will have millions of concurrent users. How do you scale? What type of backend infrastructure do you need to support hundreds of thousands or millions of users using the solution, the application at the same time? So what are the solutions that we can apply? Let's first talk about caching. I told you caching is not a database, and caching requires quite a lot of code on your side. Typically, you need to have some kind of cache inside your application. You need to query the database, put the result in cache, query the cache. I don't want to write all these boilerplate code inside my application. That's too complicated. How do you hydrate the cache as well? When the application is starting, how are you going? What is the subset of the data you're going to fetch from the database and put in the cache? That's also a lot of code that I don't want to write. How I'm going to query the cache? I want to do intelligent queries and query a subset of the data inside the cache. Too complex. So I don't want a cache. What I really want is a database. In my mental model as a developer, I would like to be able to write a struct, write a data model in my programming language, Swift in this case, but might be Kotlin, might be something else as well. And then I want to manipulate this object with new and stuff like that and delete, and just have a couple of CRUD API like save, delete, find, query. That's the maximum amount of work I'm ready to do for my app. The rest, I want it to be handled by the framework, by the libraries I'm going to use. So let me introduce one of these libraries. It's called the Amplify DataStore. It's one of the many things that Amplify can do for you. Amplify can manage user authentication with a user authentication service on the backend that manages the signing, sign up, forget password, multi-factor authentication flow. It can handle data storage, like the image you saw in the example demo that can come from Amazon S3. But one of the things Amplify really shines about, it's managing data, local data, and synchronizing this data with a backend in the cloud. So Amplify DataStore, this is the audience, this is Amplify DataStore. What DataStore provides you as a developer, it's an API. So it's the CRUD API that I talked about before. It allows you to save, query, find, delete your data. Under the hood, but you don't have to write any code to manage that, it will save your data locally on the device. So we are using different databases depending on the device. On the web, it's IndexedDB. On iOS, it's SQLite that we are using. But this is abstracted and hidden for you. You just have to deal with the high-level CRUD API. And the best part of DataStore is that it includes a synchronization engine that uses GraphQL as a protocol to interact with a backend. So every time you write something, you, the developer, write something into the data store, it will be stored locally, but it will also be synchronized asynchronously to your backend. So the data are persistent in the cloud. And that works both ways. So let's start from you, the developer. What is the flow to start using the data store? The first thing you need to do is to define your data model. You need to tell us what is an entity, what are the types, and things like that. And I said I want to do that in my native programming language. I lied a bit. With DataStore, you need to use the GraphQL schema. So you need to use the GraphQL syntax and type system to represent your data as GraphQL, which on one side is good, because if you have a multi-platform application, like running on Android, on iOS, on the web, you can start from one uniform syntax to define your data model. So for my podcast episode, I have something like this. I define an episode data being an ID, a date, an author, duration, a title, a description. You have date, int, type. There is nothing specific to the data store there. It's pure GraphQL. If you know GraphQL already, you are on at a familiar place here. If you don't know GraphQL, it's super easy to learn. It's a big mix of JSON and struct together. You can get started in a few minutes. Then you use a command line tool that will build and generate code for you. It's the Amplify command line tool that you need to install, of course, on your laptop. And depending on your project, it will generate code for Java, for Kotlin, for JavaScript, or for Swift. So it will generate a corresponding model inside Swift. You will get a bunch of classes, struct to be precise, in Swift that map the definition, the data type, the types that are mandatory or that are optionals in the struct. Notice how GraphQL impose the exclamation mark to say that something is mandatory, and there is no sign to say it's optional. In Swift, it's just the opposite. So you have the quotation mark when it's optional and no mark when it's mandatory. But this is generated for you from this. And then I can start to use that in my code. So I just create an entity, I pass parameter, and when I want to save that to the database, I just use an asynchronous method, amplify.datastore.save, and my episode. And all the magic happens behind the scene automatically for you, so it's saved locally on the local database, but it's also sent asynchronously across the network to a GraphQL API and will be persisted in a database running in the cloud for you. You don't have even to create that database, it creates it for you automatically. We are using DynamoDB to store your database, so it's a managed NoSQL database. I'll talk about the database in a minute. Same way, you can queries amplify.datastore.query for all episodes here, if you want to retrieve all the episodes for in the database. Or of course, you can have a where clause, a predicate that says I want to query a subset of my data. I want to query all the episodes for a given podcast, and then I give a podcast ID. It's like a where clause in SQL. I can delete, told about CRUD, so create, read, update, and delete. You can delete all the episodes. That's probably not something you want to do, but you can also delete with predicates, so filter, have a where clause on your delete. So what's happening in our architecture when we do that? The CRUD API that you call are forwarded to our storage engine, and the storage engine talks to a storage adapter, which is an abstraction with the specific database that we choose, so SQLite for iOS. So all the objects are persisted locally on the customer device. But at the same time, the storage engines trigger the synchronization engine, and the synchronization engine will transform the Swift data structure into a GraphQL API call and call a query or mutation, as they call it on GraphQL, to create, update, or delete the data on the server side. The sync engine also subscribes to the AppSync server, the GraphQL server, to listen for change. So it's a WebSocket call that is persistent, that is entirely managed by the library, to to listen to change as they happen on the server side. So you have really two ways communication. One way is from your application to the GraphQL server to write your data into the cloud, and one way to listen to change as they happen in the cloud, maybe made by another user or the same user with a different application. And you can subscribe, you, the developer, the application can subscribe to these change to be notified when something happens, and that's the real-time part of Amplify. That's my favorite feature of Amplify. It's one API call, it's called observe query. So instead of query, it has all the same syntax, the same parameter as query, but it's observe query. So instead of returning a snapshot, a one-time snapshot, it returns a stream of asynchronous data. So it's an asynchronous stream which is returned from that. It means that you, as a developer, you can write a for await loop that will continuously loop as long as events are provided by this stream. If there is nothing in your cache, because it's the first time the user starts the application, this thing will hydrate the local database as well. So it will fetch the data from the server side, populate the local database, and then stream the change as they happen on the server side. So to consume that, you just need to create a for await loop. That's a for loop that will never finish unless the stream is broken, like there is a disconnection, for example. But that loop will continuously poll my load podcast method, which is calling the other one I show you, the observe query, and return results as they are coming back. And then you somehow change your state, and if you change your state, it will refresh the user interface, at least with SwiftUI. So that's the way I architecture this type of application. I have a view, I call it a model, but it's not really a good name for that, but it's somewhere where the state is maintained and there is an API to change the state. And then there is the backend class, as I call it, that is responsible for the communication with Amplify DataStore. So one line of code, and you poll for events happening on the server side. Okay, now the fun part. What if there is a conflict? Because you have been offline for a period of time, you change something, someone else changed the same data. How are you going to detect that there is a conflict? How are you going to act on the conflict? The good thing is that you don't have to write any code to detect conflict. And in the majority of the case, you don't need to write any code to resolve the conflict as well. It depends on your conflict detection and conflict resolution strategy. You might write code if you want to change the default from Amplify, but by default, it does a pretty good job at trying to merge the change as well. How do we do that? On top of the schema that you provide, remember the GraphQL entity and the Swift struct. On top of that, we add a couple of additional fields. We added, like, for example, a version ID and timestamps. When did you change that? When it was last changed. So we know what is the version on the backend, what is the version on the client side, and we can compare versions. So if there is a conflict in version, like you have version 3, but on the backend is version 4, we can detect that there is a backend. And the timestamp is going to help us to detect what is the correct change, which one is the one you want to keep. How does it work in the details? So the conflict resolution strategy by default is trying to merge data. And you will see for most conflict it works, and for most application it's acceptable. But of course we understand that sometimes for other application, you might want to change that. I will show you how to change that. But let's have a look at auto merge first. So let's imagine you have one entity, a person. Her name is Jennifer, and she's 32 years old. Then we have two customer applications that are making change on that entity, person Jennifer, age 32, and both customers are adding a field called title, one of them as engineer and the other one as a developer. What do you think is going to be the final result of that merge? Any idea? Ding, ding. Actually, auto merge keeps the last change by default. So the last one that talks is the right one. So I see you're scratching your eyes there. Maybe it's not good for your application. I'm not telling that it works for all applications, but for the majority of applications, it might work. And you might implement different strategy, and I will show you how to implement different strategy as well. But this is the worst case. This is the case where two customers are modifying the same properties. Ooh, I should not tap on the screen, the same properties for the same entity. There are a lot of other cases where auto-merge actually makes a lot of sense. Imagine again, we have a person, Jennifer, 32, and we have two customers, and this time they are changing different properties, like client A adds a title property and client B adds a location property. What do you think will happen as the merge? Yeah. We can keep both because this is not conflicting. Yes, we are modifying the same entity, but we are not modifying the same field. So we can actually merge, and the result version will have the two properties. Same with lists. If Jennifer has a property called hobbies, which is a list of different hobbies, and two customers are changing that list, as long as they are changing different values in the list, we can merge without any conflict. So the resulting list will be climbing, karaoke, and reading with the two change from client A and client B. So DataStore implements a conflict detection by default by using versioning. A version is just a counter that we increment at each and every change. And DataStore relies on AppSync. So actually, AppSync is the one, it's the server side that controls that and that manage the versioning and the detection of the change. It's also use different techniques in the database to be efficient, to detect all the change. So one of the things we do, we store that version on the database as well. So if you go and look behind the scene in the database that is being created for you, you will see that there is an extra field that has been added, that _version. And every time one of your customers is changing an entity, so here we have person ID 100, age 30, age 31, age 32, every time we increase the version automatically. You don't need to write code for that. That's the main table, but for each main table where we store your entities, we also transparently manage a change table. And a change table is like a log of everything that happens on your entities. So if you create, update, or delete something, we are going to add records there with a special primary key and secondary key made of the time name and the date and the timestamp at which the change happened, and the version as well. The version is kept, and the timestamp of the last change. So this change table allows us to trace the history of everything that happens on an entity, including deletion or changing something, because we don't delete lines there. That's not entirely true. We clean up that from time to time. I will explain that later. But we keep adding stuff there, so we can recreate the entire history of what happened on a specific entity. So let's take another example. We have two customers, customer A and customer B. They are using your application, and they both start the application and download a person, age 32, version 1, onto their device. Okay, that's the state of the database. Everything is well synchronized so far. User B changed the age of the person, and version 2 is created on the device of user B, and that state is propagated to the database. So now in your backend, it's age 33 and version 2. And of course, user A received a notification from that with the observe query API I was talking about. So automatically DataStore will download that new version for user A as well. So everything is perfect in both worlds right now. Everything is synchronized. But at some point, user B goes offline. Oops, he's in a tunnel, in a train. And of course, user B continues to use the app. It doesn't even realize he's offline. He's changing the person. Now the age is 34. He adds a property. Location is Seattle. And local version is 3, but user is offline. So that local version is never propagated, or it's not propagated right now to the database. Yes? Do I still have everybody with me? Okay, I see you nodding. Of course, we don't live in a perfect world, so during the same time, user A continue to work with the app and generate age 35, which is a conflict with 34 here. and they both have version 3. That version 3 is also pushed to the database because user A is online, so the synchronization happens with the backend automatically. And what must happen happens. At some point, user B comes back online. So what is going to happen? What is the final version? And what will be the data there? 35? Anyone else voting for 35? Yes? The majority? Yes. And of course, location Seattle can be merged. So remember, the last one that talks is correct, or the last one that talks has authority. And if this is the time, this user talks after this one. So this one has authority as well. So the final version will be version 4, not 3. And it will have the last change, 35, location Seattle, version 3, and of course both can reconcile and reconnect. So that's the final version of the data. I told you, for most applications it might be acceptable. Of course, you might develop application where the data model is a bit more sensitive. The extreme case, of course, is payment. You don't want that to happen for a payment. The last one that talks is correct. So you might have different strategies as well than the one that we implemented by default called auto-merge. So what are these other resolution strategies? Auto-merge, I talked about that one already. There is another one called AWS Lambda. AWS Lambda is not a conflict resolution strategy. It's a service from AWS that allows you to deploy function as a service. So you just write a function, you give us the code, and we run the infrastructure for you automatically. You don't have to install Linux, Python, or anything else. You can write function in Python, Java, TypeScript, Node.js, Go, Rust, Swift as well. So what happens with Lambda there? If you choose for that type of conflict resolution strategy, when AppSync detects that there is a conflict, AppSync will call one of your Lambda functions. So you have to write code. It doesn't happen automatically. You write code. And your Lambda function will receive two parameters, version A and version B, so the two different versions that are in conflict. So you can write code that will inspect the data structure for these two versions and decide what to merge. And you return the response of your Lambda function is the merge result. So it's entirely up to you to decide which one is the correct one. How do you do that? We don't want to know. You just receive the two, and you have to take a decision and give us the result, tell us what is the final result. You can call other API, you can send push notification to the user, really up to you. The other one, it's a bit easier because there is no code to write. It's called optimistic concurrency. And the idea with optimistic concurrency is that remember, we have a version field. So I have version 3 of something. I change something. So my local version becomes version 4. So Amplify DataStore is going to try to write version 4 to the database. And the system, AppSync, will accept the change only if in the database it's still version 3. If it is version 4 or higher, it means that someone else changed the same data while my user was changing it locally. So the data is not current anymore. The data that I have locally is not up to date with what is on the server. And with optimistic concurrency, we detect that and we reject the change. It means, what does it mean for you as a developer? It means you receive an exception, saying, hey, we cannot synchronize. And again, it's up to you to decide what to do. Typical strategy means refreshing the data that is from the database so that you know what is the current version. And then it depends on your business logic. It might be auto-resolved. You can merge by writing code on the client application and then try to save again. Hopefully nobody will have changed the data anymore and that save operation will succeed. Or you might pop up a sheet to the end user and say, hey, this is the type of conflict I have right now. Which of the data do you want to keep? What do you want to change? But that logic is entirely yours. It's up to you to define something. So if I have to summarize, we do the merge automatically for you the best we can. Of course, if there is a real conflict like changing the same data on the same entity, we have to find a rule, and the rule is the last one that talks win. You resolve the change on the server side on AWS Lambda in the cloud. And you resolve the change, the conflict on the client side. Inside your iOS application. That's basically the three options you have to resolve strategies. How does it work with synchronization? Let's imagine that I've been offline for 2-3 days, and then I start the application again. I want to know what's happening in the world. I don't want to continue to use my old data that are stored locally on the database on the device. We make that super efficient. Again, it's transparent for you as a developer. You don't need to write any code, but what the libraries does under the scene, it uses the base table. But of course, reading the entire database and the base table might be super inefficient. We might have thousands or tens of thousands of records there, so we don't want to bring the entire table back to your application. So what we do as well is to keep a log of everything that changed on the server. So imagine we have our 2 customers, one of them goes offline, and while this one is offline, the other one deletes user 102. So that line disappears. So how this one can resynchronize, how this one can know that actually there are some data that are disappear. Adding data, it's quite easy to detect additional data, but data that disappear, you would need to compare everything one by one. So to help for that, we use the delta sync approach. Remember, we have a lock. We have another table that logs all the change that happen on your entity. That's the change table. So if you delete something or if you add something to the base table, it will be logged in the change table. And the change table has an attribute that says when it was changed. So if our user goes offline there and something happens to Melissa, for example, we add something as an entity or we delete something as an entity. When the user comes back online, he's not going to resynchronize the entire base table. It will just make an API sync to say, hey, please give me all the change since I've been offline. And we use the date and the time, which is part of the index, which is there as well, to know the exact list of change that happened on the entity. So the library does that for you. You don't have to care about that, but the library, instead of querying all data from the base table, is going to make just a delta sync. Give me all the change that happened since I was last online. And that's how the application and the library can know what happened. It can also know if something has been deleted, because if you delete user 102, Melissa, we have a flag there that says, hey, it has been deleted. And in the change table, we also add a flag saying it has been deleted. So the sync, the delta sync query can also give you the list of entities that have been deleted, and the library will delete from the local database the entities that have been deleted in the cloud automatically for you. But then, of course, you're thinking, hey, if I'm deleting a lot of entities, I will keep that in my database, and my database will keep growing and growing. And in the cloud, you pay for what you use. So if you use more storage, you will pay more for that. Obviously, you don't want that. So we use a feature of the database to help us to clean the database automatically. It's called a TTL. TTL stands for time to leave. It's a special field that you give to DynamoDB, the database, with a timestamp. This is an epoch. So the number of seconds since 1st of January 70. And when the current time is bigger than this, the database will automatically delete this line for you. So again, there is no code to write from your side. There is not even code inside the Amplify library on the client side. It's automatically done. That type of housekeeping is done automatically by the database with the time to leave. And if you want to change the default time to leave, of course, you can do that. By default, it's very short. I was surprised. It's like 1 day or 2 days. So it means that if I restart my application after 1 week or 2 weeks, I don't get this data. I don't get the sync. I need to do a full resync anyway. So really, depending on the behavior of your user and the type of data you're storing for your user, you can use an option to change that to 1 week, 2 weeks, 1 month. It's a balance to find between the cost of storage versus the initial resync operation for your user when they come back online. So what are the platforms where you can use Amplify and the Amplify DataStore? I told you we support the web, of course, with React, Angular, Vue. We do support cross-platform environments such as Flutter. Flutter, it's available now for the web, for desktop application, and for mobile application on iOS and Android. We do support native Android as well with Kotlin and Java. and native iOS with Swift. So there is a native library that you can use with just adding a line in your package manager or inside Xcode to get started with Swift. If you want to know more, online there are two places, docs.amplify.aws and the Amplify community on Discord. It's quite large and super active, super friendly and inclusive community where you can ask your question. Many people from the Amplify team are there, and most of the time you get the answer by the person that wrote the code directly. So that's quite interesting as well to have first-hand source for that. Remember also, Amplify is much more than just the data store. I choose today to talk just about the data store, but we can also store your image or video in the cloud, take care of user authentication, send push notification, plus all the things that I didn't mention, but that are available in Amplify as well. If you want to have a look at the SwiftUI data store demo, the mini podcast application and the synchronization there, it's on my GitHub, github.com/sepstore, and then you search for Amplify data store, and you will find a couple of sample codes that you can get started with. And I'm ready to take questions.